Good evening. Welcome to EEFIT's Research Grant Winners Showcase 2025. For those of you who don't know me, my name is Yasim Naktash, and I am the chair of the Management Committee of EEFIT. It is my honor and a privilege to be chairing this event tonight. Although EEFIT has an incredibly wide international audience, and I am sure many of you already are familiar with our group, I thought that I would start with a little bit of an introduction as to what EEFIT is and what our aims are for those of you who might not be as familiar. So EEFIT is a group. The Earthquake Engineering Field Investigation Team is a specialist group that has been operating under ISTRAC-T since 1980s. With the aim of carrying out detailed technical evaluations and collecting perishable data from post-disaster sites to assess the effectiveness of repair and retrofit and to study the disaster management procedures. Among all this, we are studying not only the built environment related characteristics or impacts of disasters, but also are looking into social and economic effects of earthquakes and tsunamis. But also we are quite interested in understanding the effectiveness of response and relief operations and the short to long-term recovery. For all of these, the activities under our remit is, of course, first of all, mission work, both the immediacy missions, but also return missions, sometimes to be able to gauge, again, our understanding of the recovery processes. But also we do organize training courses to train the next generation of disaster risk management professionals. We stay embedded within the international post-disaster reconnaissance communities. That's very important to us. We are quite focused on capacity sharing with the strategic disaster management stakeholders and partners worldwide. And we really wish to influence disaster resilience policies through our outputs, including reports, consultations, and research. Recently, we also started to incorporate increasingly advanced technology into our missions, such as remote sensing products and machine learning and AI. And we are using the field work and the data that we are collecting through field activities to develop, pilot, validate, and verify these technologies. Just a few of our most recent missions and reports coming from 2023. We, of course, have completed a very large-scale mission work to Turkey earthquakes, which included one full-on visit to the site and then subsequent smaller-scale, more specialist field work. We have completed our Morocco earthquake, and we are about to release our report very soon. We have completed a return mission to the Indian Ocean tsunami event and the affected areas. And again, please stay tuned for the report from that. We have very recently published a report following the Myanmar earthquake with colleagues from the States, Myanmar, and Thailand. And I am very pleased to announce that EEFIT is currently collaborating with the French and Pakistani colleagues to develop a remote report on the Afghanistan earthquake and its impacts. And please stay tuned for that report. Now, this is, however, about the two research awardees and their work. So you are going to hear from both of them tonight. While listening to them, please at any point use the discussions and chat feature to ask any questions that you might have. If you have any technical problems during the event, please reach out to the events team using the email address that you're seeing here. Also, please be reminded that the recording of this event is going to be made available on the ISTRAC-T website in a couple of weeks' time. I was also asked to read this copyright statement. To the institution's best knowledge, copyright permission has been provided for all material shown, and this broadcast is therefore presented in all good faith. If the copyright holder believes permission has not been forthcoming, then the relevant item will be removed, or by agreement an appropriate acknowledgement provided to accompany the recording post-events. With this, I am very honored to present our speakers tonight, Furkan Narlitepe from Istituto Universitario di Studi Superiori, and Dr. Anca Ciupala from the University of East London. Furkan is going to talk about rapid earthquake assessment under uncertain conditions. And with this, I would like to leave the floor to Furkan, please. Thank you.
Thanks a lot, Professor. Hello, everyone. Today I will talk about our project, which is titled as Rapid Earthquake Assessment Under Uncertain Condition. Before I start, I want to say something. Of course, first, thanks to EEFIT committee for giving me this opportunity. And another amazing thanks to my supervisor, Professor Vitor Silva, for his amazing support. And the last appreciation for you who are interested in and join us for this event. So let's start with the main motivation of our research, and let's talk what is the exact problem that is investigated in the study. After a devastating event, a rapid earthquake impact assessment procedure provides some ground shaking and loss estimation. And in overall, when an earthquake happens, this assessment procedure basically rely on three well-known inputs. For example, first one, ground shaking estimation in the region of interest. And the second one is exposure model of the region. And the last one, suite of vulnerability function to calculate expected losses condition on specific IM value for each building typology in the exposure model. While the second and third one can be prepared in advance, it's really challenging to get ground shaking estimate with the best clarity, because the accurate ground shaking estimates are exactly correlated with the knowledge of the rupture geometry that you have. But unfortunately, nobody knows about the exact rupture geometry in the first moment of event, especially if you have a devastating event. So that's why the rupture geometry is the major contributor of the uncertainty in the ground shaking and accordingly the impact estimates. For example, there are many automated and non-automated rapid impact assessment platform providing valuable information and estimates for the losses. But after a destructive event, unfortunately, we have blind hours, which means we cannot effectively assess the event's impact. And therefore, in such hour, we have to benefit some simplification and approximation. Please look at the USGS pager updates released for 6 February 2023 Kahramanmaraş earthquake. And as you can see, in the very early version, rupture could be identified with a point using basic super characteristic, such as magnitude and depth. But once we get more information about the rupture geometry and orientation, the rupture can be identified much more realistic, and this exactly affect the loss estimates. So in the study, we are investigating this discrepancy from rupture geometry uncertainty and its potential effect on both ground shaking and impact estimates. And for this investigation, we are using different rupture modeling approaches such as point source, planar rupture, pre-calculated rupture model, and the complex rupture model. Then we tested these modeling approaches in real-world example that occurred in the different region and different magnitude. And we obtain the estimates for the different impact metrics, such as economic loss, number of fatalities, number of completely damaged building estimates. And at the big final, for each scenario, we compare the estimates that come from point source, planar and pre-calculated rupture model with the complex rupture model that serve as benchmark rupture to evaluate accuracy and reliability of the impact estimates. So we believe that the results I will provide in this presentation will be quite useful for not just national authorities and also international, in particular when there is an urgent need to deploy rescue teams and other human resources after a disaster. So let's start with the input model. As I said before, in the study, we are using 5 earthquake scenarios that have distinct magnitudes and occurred diverse tectonic regime. And as you can see in this project, we have iki Kişili earthquake, Kahramanmaraş, Turkey, Kumamoto, Japan earthquake, L'Aquila, Italy, and Lorca, Spain earthquake. And these earthquake examples were intentionally chosen to cover some criteria. For example, as you can see, our scenarios have broad range of magnitude from 5 to 8. And also some of them are inland earthquake that happen beneath on urbanized area, and one of them is offshore events. And more interestingly, one of them has a complex rupture with arcuate shape, while the complex rupture pattern of some has a planar geometry. And also, last but not least, in the regions of earthquake scenarios vary in terms of construction practices. For example, Turkey and Italy have vulnerable building exposure, but in Japan, code compliant building constitute vast majority in the building exposure. So once deciding these scenarios, second step is to identify rupture models for each scenario. First one is, of course, the point source approximation. This approach is commonly utilized in initial version of the rapid impact assessment platform, and it's rely on generally limited information and accordingly exhibits significant uncertainties. Due to the scarcity of the data immediately after an earthquake, the calculation is primarily based on earthquake's magnitude and location. And the second rupture modeling approach is a planar rupture model. And this one is essentially relying on focal mechanism solution, I mean strike deep and rake angle, obtained from international and national seismic agency. This modeling approach is a representation of more constrained rupture geometry compared to the point source approximation. And the third one is the pre-calculated rupture model. In this rupture modeling approaches, we are leveraging ruptures generated from seismic hazard model, because these model can simulate thousands of potential ruptures by considering geometry of the fault source or parameters associated with the area and point source. Then we just basically picking up most suitable rupture based on hypocentral location, magnitude, and focal mechanism of the event. This collection of the rupture is commonly referred as earthquake rupture forecast. And when an earthquake occurred, this approach offers an advantages, potentially providing a realistic rupture within minutes of earthquake. And the last option, which serves as a benchmark solution in our project, is the complex rupture model. And this represents most sophisticated and accurate rupture model, because this is generally rely on finite file solution that requires intense analysis. Second leg of the input model for the risk analysis is exposure model, of course. And in this study, we are using global exposure model developed by Catalina Yepes et al. And this model is not covering just residential building, but also commercial and industrial building with various resolution level. The maps that you see on the right-hand side, you can see special distribution of number of building in the exposure model. And then you can also see the economic value of the building exposure. So for more information, you can use the QR code to reach the publication. Last input model is shear fragility and vulnerability function. And in this study, we are using global fragility and vulnerability database developed by Martins and Silva. Again, I attached the QR code to directly reach the GitHub repository of the specified publication. Basically, to obtain loss and damage statistic, we adopt this function for each building class in our exposure model. On the right-hand side, you can see some example vulnerability curves that show expected loss ratio based on condition IM for structural, non-structural, and building content components. Since we compiled all input model, we are ready to run these scenarios using OpenQuick engine. In this slide, I try to show our methodology with a flowchart, and let's see what we are doing, and more importantly, how we compare discrepancies of the rupture model against the complex rupture. For each scenario, we are basically doing analysis using exposure, site, and vulnerability model, along with the distinct rupture modeling approaches. Then we are obtaining impact assessment results for each rupture model. In this stage, we have quantitative data for each risk metric, such as loss, number of fatalities, number of completely damaged building estimates. And using these data, we are comparing the performance of each rupture model with percent differences of the estimate. For example, let's talk on the number of completely damaged building. For example, please look at the formula on the top. and E represent the estimates that come from the simplistic rupture model, which means point source or planar rupture model or pre-calculated rupture model. And R corresponds to the estimates from the benchmark solution, the complex rupture model. This is basically percent difference calculation, and it allows us to show discrepancy of the rupture model in each administrative division. Another way to evaluate differences that we present in the further slide is to use regional weighted difference. To obtain this value, please look at the formula below. We multiply percent difference by the number of completely damaged building estimates. Then we sum up these values across all region and divided this total by the sum of all completely damaged buildings to get final average. This is really useful for evaluating performance of the modeling approaches, not in the administrative division across all region. So, Sophia, could you please go another slide? Yeah. Before the scenario-based analysis, we want to start to investigation of the impact of different rupture modeling approaches in the arbitrary region, because we believe that before the scenario case, this will be useful to cover and understand overall purpose. For this analysis, we choose 100 times 100 kilometers square arbitrary area and assumed a hypothetical fault at the center of the region. And then we generate a suite of earthquake with a magnitude ranging from 5 to 7. For the simplicity, focal mechanism solution were identified as the same. And also, for the sake of simplicity, again, a uniform soil profile was assumed across the study area to neglect site amplification effect. Then, using the rupture distances for each earthquake, PGA values were estimated. And more importantly, these estimates that come from planar rupture geometries compare with the ones coming from point source rupture model. So let's check the results. Please look at the figure. It shows the PGA estimates for point source and planar ruptures for each earthquake, and also the percent differences in each grid cell. And as you can see, if you have a low magnitude events, the point source and planar rupture model estimates are quite similar. And also, of course, in overall planar rupture model produce a wider distribution of strong ground motion, especially if you have a high magnitude events. And also, if you focus on the epicentral region, in the epicenter, PGA estimates remain unaffected by the rupture modeling approaches, because if you check the results in the epicenter, percent difference is around 10%. But if you go further from the epicenter, in that moment, rupture geometry significantly influence the ground shaking up to 50% for the moderate event or 80% for the high magnitude events. So for the investigation of impact of rupture modeling approaches on the loss estimation, we follow some assumption for the sake of brevity. First, we are assuming that two-story unreinforced masonry building exists in each cell, and generic replacement cost is equal to $1,000. For the economic loss estimate, we are following two scenarios. Scenario 1, a settlement with a uniform building stock located directly above the earthquake rupture, because we know some urban centers located directly top of the active fault or near to active fault. For example, Manila from Philippines, Wellington in New Zealand, and Quito from Ecuador. So as you can see, for these settlement scenarios, when the rupture identified as a point source, relatively small discrepancies were observed for an 5 magnitude event, but this increased significantly for larger magnitudes. So we can say that for scenario A, percent difference is relatively small in the center, because hypocentral distance and rupture-based distance are more or less the same. So That's why we can say that when an earthquake happened in the top of the fault, an epicentral cities of the event does not affect so much from the rupture modeling approaches. In the case of scenario B, which represents a settlement with a uniform building portfolio located 30 kilometers away from the earthquake rupture. This scenario is also quite useful because some urban centers located within a similar distance to active fault, for example, Istanbul from Turkey, Chengdu from China, and Kathmandu in Nepal. The impact of rupture geometry on the loss estimates in this case is slightly reduced. Please look at the case of magnitude 5 earthquake. And in this case, estimated losses are low regardless of the rupture geometry, and the difference is below 13% between two approaches. On the other hand, for the 6 magnitude events, although the rupture geometry become noticeable, percent difference only increased to 30% for the grid cell closer to the rupture. And finally, for the 7 magnitude event, rupture geometry has stronger impact and accordingly resulting in substantial losses and percent difference above 50%. So let's go back our scenarios. This slide is just kind of reminder that shows which earthquake scenarios we are interested in. So we can proceed with each of them in order of the magnitude. For example, first scenario is Ikiki-Shili earthquake. As I said before, this earthquake with a magnitude of 8.2, and it's quite important of Shili's recent history. This event was generated a truss faulting mechanism at the depth of 25 kilometers. Depending on the official statistics, 8,300 houses were damaged with varying degree. The map at the right side is showing the spatial distribution of PGA estimates. But before speaking about this map, I want to clarify something. Ground shaken was calculated on 4 times 4 kilometer grid, but only the grid cell where assets or population exist were considered. So as you can see, the point source approximation has led to a significant underestimation of the ground shaken. And planar and pre-calculated rupture models are much more realistic and compatible with the pattern of estimates coming from the complex rupture model. Let's look at the impact results. If you check the impact results, aggregated losses reveals that major differences between model. Please look at the total row. The point source approximation proved highly inaccurate with the total of 20.2 million US dollar estimates. It is almost equal to 100% differences. And planar and pre-calculated rupture models resulted more consistent and realistic results with 2.1 and 2.3 billion US dollar in the differences rate, 12% and 20% differences respectively. And overall, pre-calculated rupture model provide best performance for this specific offshore event. So let's continue with the Kahramanmaraş earthquake scenario. This is an earthquake sequences with the magnitudes of 7.8 and 7.5, and it struck southern Turkey and even Syria. And this event was a consequence of strike slip faulting mechanism in the North Anatolian fault zone with a shallow depths. And based on official reports, totally 11 provinces were affected, and unfortunately 50,000 people died, almost 30,000 building collapsed, and so on. So if you look at the map, you can see the spatial distribution of PGA for different rupture modeling approaches. So according to the result, point source approximation again is not successful to catch size of the earthquake impact. As the second modeling approach, planar rupture model is not bad for the estimates compared with a complex rupture, especially the upper part of the rupture. But again, as you can see, pre-calculated rupture is quite fantastic because it's catching almost all parts of the complex rupture. So let's go to the impact estimates and let's see what's happening in the loss part. And as you can see at the aggregated level, again, please look at the total row. Point source model estimates 7.3 billion, and it is equal to almost 61% difference compared with the complex rupture model. And planar and pre-calculated models are more consistent and accurate, showing much higher estimates, almost 20 billion US dollar, with a difference rate 2% and 7% respectively. But if we talk about the regional analysis, and as you can see, regional weighted differences reveals a key insight. For example, pre-calculated rupture model is the most accurate overall, with the lowest total discrepancy of 15%, because planar rupture models' accuracy drops significantly at the regional scale. So let's continue with the third example. It is Kumamoto, Japan earthquake with a magnitude of 7 and occurred in the Kumamoto prefecture as a consequence of strike slip earthquake at the shallow depth again. And according to the official figures, these events caused the damage with varying degree in almost 190,000 buildings and almost 200 fatalities and almost 2,700 injuries. Also, this event triggered secondary hazards such as landslide, debris flow, slope failures, and so on. So please look at the map to see spatial distribution of PGA, again for different rupture modeling approaches. As seen in this figure, the point source approximation, higher PGA estimates are significantly localized at the epicenter, and the impact area of the ground shaking is quite narrow in the region of interest. But in contrast, in the planar rupture modeling approaches, impact area includes attraction and covers a larger area, unlike the results obtained from point source approximation. Besides, as you can see, PGA distribution pattern is quite compatible with the ones coming from complex rupture model. As for the pre-calculated rupture model, it produced similar distribution pattern compared to the point source model, but of course, there is a spatial orientation and special rupture geometry, because pre-calculated rupture model has rupture geometry compared with the point source approximation. Let's go ahead with the impact assessment for this scenario. And as you can see, while the planar model matches with the pre-calculated model's accuracy in the aggregated level, which means you can check the total rho, but the regional analysis is crucial for identifying the best performer, because if you look at the regional weighted differences, pre-calculated rupture model proves to be superior because it has highest precision across all regions with a low 13% discrepancy. Fourth example is very well-known L'Aquila, Italy earthquake. It is earthquake with a magnitude of 6.3 and struck L'Aquila in central Italy. And it's a normal faulting event, caused the catastrophic damage and resulting 300 fatalities and displacing much more people. The region suffered extensive damage to roughly 60,000 buildings, and including its vulnerable historical center and critical infrastructure. So if we talk about the effect of different rupture modeling approaches on the ground shaking estimate, as you can see, unlike the other earthquake example, the L'Aquila event shows the relatively minor variation in spatial distribution of PGA across the rupture model. This may be attributed to its moderate magnitude, and the impact area remain largely confinement to the epicentral region, regardless of the modeling approaches. And overall, point source approximation produces higher PGA values strictly at the epicenter, but planar and pre-calculated rupture model extend these higher intensity range over a slightly wider area as a consequence of specific rupture geometry. And the complex rupture model also did not generate much different PGA distribution pattern when compared with the other simplified approaches. So again, we are going to the impact estimates. If you check the total rho at the aggregated level, if you look at the total rho, the planar and pre-calculated rupture model provides most accurate loss estimate around 2.7 billion US dollar. But the calculation of the differences at the regional scale reveals an important distinction. For example, planar rupture model proves to be most consistently accurate with a low discrepancy rate, which is equal to 11% across all regions, but pre-calculated rupture model's accuracy decreased with 21% difference rate. So the last scenario is the Lorca earthquake with a magnitude of 5.1. It is really useful to demonstrate how a low to moderate event can have severe consequences. According to the official results, it caused 9 fatalities, injured 400 people, and triggered extensive damage, including partial collapse of a vulnerable masonry building. And as for the impact of the rupture modeling approaches on PGA estimates, there is nothing to say so much, to be honest, because the results is telling us if you have such low magnitude event, rupture modeling approach is not an issue, is not much an issue, because please remember this inference is quite compatible with the results that we talk on arbitrary region. Maybe you can ask why there is no pre-calculated rupture model. That's a good point. For example, yes, why we don't have pre-calculated rupture model? Because available fault source in the seismic hazard model that we use in the study cannot sufficiently represent such low magnitude events. That's why we exclude pre-calculated rupture model for the Lorca example. If we talk about the loss estimates for the Lorca earthquake, as you can see, point source has highest differences as always, but please check the difference rate. It's just 38%, not as high as we see in the other earthquake example. And if you talk about the planar rupture model, is quite successful because it produced a loss estimate very close to the complex rupture with only 5% difference. This accuracy is really good point because during the presentation we are telling us the planar rupture model is a simplified rupture modeling approaches because it's essentially rely on focal mechanism solution, and of course the results can be changed when more information and finite solution are available. But this analysis telling us at the low magnitude event, planar rupture can be quite useful without waiting for the complex rupture solution. So actually, it's the last scenario that I will present today. So let's conclude. In the study, we evaluate how different rupture models affect rapid impact assessment using 5 past earthquakes, and we compare 3 simplified methods against a detailed reference model, rupture model, across events of varying magnitudes and the regions. By analyzing differences in the ground shaking and damage, we have developed key recommendations for improving future assessment. For example, moderate magnitude events with epicenters far from the populated area can be effectively modeled using a simple point source. And also events near or beneath urban areas require more detailed rupture modeling approaches regardless of the magnitude of events. Point source model can underestimate impacts by up to 50% for the moderate event or up to a factor of 2 for more stronger earthquake. And the planar rupture model typically provides acceptable results, as I said before. However, automated or non-automated systems are need to be select correct nodal plane, ideally supported by national or global active fault database. And also in the regions with acute fault system, for example, Middle America Trench and North Panama Deformed Belt, in this region, planar model often underperform, especially at the subnational scale. Ruptures informed by the seismic hazard model, which corresponds to pre-calculated rupture model in our project, can greatly improve impact estimates in the regions with complex fault geometries, but it should be noted that their effectiveness depends on the hazard model completeness and accuracy. Even in well-studied area, a typical rupture may deviate from the model expectation. For events of small to moderate magnitude, the use of ruptures from seismic hazard model is unlikely to be beneficial or even feasible because this type of seismicity is often modeled using area source rather than fault source. So in such case, planar rupture model informed by the correct nodal plane are expected to the better perform. So we believe that the outcomes from this research can be useful national authorities and international organizations to remit to calculate and communicate earthquake impact shortly after their occurrence. And more importantly, such results are also quite useful for the scientific community, which is often responsible for developing and operating rapid loss assessment platform, because this finding will be considered when assessing losses and damage within the rapid impact assessment framework of the GEM Foundation. This platform informs several humanitarian communities about the expected impact of disruptive events. And we have a disclaimer. The impact analysis presented in the study assume that the exposure and vulnerability components are quite accurate, but as discussed, and it's very well known in the literature, the reality is that incomplete, bias, or outdated exposure and vulnerability model can considerably affect the impact estimates, often introducing deviation greater than those caused by the rupture modeling approaches presented in the study. So this is actually last slide from my side. Thanks a lot for your attention.
Thank you. My name is Anca Ciupala. I'm going to give a presentation on identification of seismic damage states in reinforced concrete residential buildings, a deep learning approach, as part of the EEFIT research grant scheme 2024. I'm very happy to be here. And I would like to thank EEFIT committee for this opportunity and for you to attend this event, for attending this event. I would also like to acknowledge the contribution that Mr. Kabisha Besuria had to the preparation of the required materials for this event. In terms of outline of my presentation, I will talk you through the brief introduction, a research methodology adopted in this study about a unified element level damage state identification criteria, about a few words about database development, about multi-model deep-based learning model, a few words about the assessment of the evaluation of the performance of the model, and not in the end, a few words about the limitations and future research directions. So, as you know, in terms of problem statement, as you know, large earthquakes leave authorities with a significant amount of buildings in need of structural damage assessments. When these damage assessments are slow or inconsistent, they undermine life safety of occupants, reoccupancy of the building, and recovery process in general. So the key need here is not only just speed up the damage assessment as such on their own, but speed up with accuracy and procedural consistency, so the results can be trusted and executed. So this study will directly target this gap. Okay. In terms of scale of impact, I will give you just. I will talk you through I will give you just the examples of two examples in terms of earthquake, because Furkan presented a lot of earthquakes beforehand. So I will talk about the 2011 Japanese earthquake and a more recent earthquake in Turkey, 2000 and 2023. So in these figures, you can see the significant level of destruction, a significant level of waste generated. So, or in other words, you can see the economic cost, and on many occasions in the earthquake, the social cost in terms of people being displaced. In terms of frameworks, such as post-disaster needs assessment framework will mitigate these losses, these challenges mentioned beforehand through assessment protocol, but they will. There is a need for rapid and accurate seismic structural damage assessment method, not only to determine the safety, occupancy, occupant safety, but and usability of the building, but to capture the structural integrity data needed for retrofitting strategies, for example, or for interactive improvement of building codes and damage assessment guidelines before, thus strengthening resilience before the next event will happen. Okay. In the context of how data is used for damage assessments using AI, we have identified in the literature two main methods, vibration-based and image-based. In the vibration-based method is processing sensory information from the building, coming up with the damage state of that building, or the second type below, the vibration-based, which is image-based damage assessment method, which is processing images, coming up with the damage state. The aim of this project is to look at the image, so the image-based method, so the second method. The impact created by this study is threefold. So first of all, to develop and identify unified identification criteria at element level. This will be aligned to current design codes and guidelines. And then with that, develop a model, assessment model, a deep learning model for rapid classification of damage. And with that, having this model, assessment model, we can identify structural failure modes and subsequent failure mechanisms in damaged residential buildings. Just to highlight that we looked at only two failure modes, so the flexural mode and shear mode. Okay. We placed our study in Turkey because of the high seismicity. So you have here the seismicity of Turkey. The focus of this project is on reinforced concrete frame building, residential building structures with unreinforced masonry infill walls, which are common, which is a most common type of concrete buildings in Turkey. In terms of intervention strategy, we started by looking at, we start by identifying, by inspecting the field photos of damage structural elements, and then identifying the governing failure mode, so in flexural failure or shear failure in this particular case, using deep learning model, deep learning based assessment model. We noted that some of the researchers prefer to determine the level of damage. Some of researchers prefer to identify indicators in terms of structural integrity, but some of the researchers prefer to look at classification aspects. So the first part, in terms of failure mode, the classification at the element level would be the focus of this presentation. Regardless of the approach taken, we can evaluate based on that. We can evaluate the structural integrity of our building, and we can make decisions about the fitness, the occupancy fitness, or the need in terms of retrofitting of the building. In terms of failure modes, I mentioned earlier on that we talked about, in this particular study, we looked only at flexural failure mode corresponding to ductile behavior, and shear failure corresponding to brittle failure in columns, beams, and unreinforced masonry infill walls. It's just to say that why, perhaps you will wonder why perhaps we looked at only two failure modes, the flexural modes and the shear failure modes, because we try to the practitioners will try to distinguish between the elements. If an element still has rotational capacity, for example, or can bend, or can dissipate energy, for example, flexural failure, or lost completely the strength, for example, corresponding to shear failure. In terms of research methodology adopted in this study, so we developed, as I said, first of all, a unified identification criteria at element level. We developed afterwards the database, a target database. We developed a multi-model deep learning as model, and we evaluate in the end the performance of this model. So in order to come up with, to identify this criteria, we performed two workshops, were conducted in Turkey, so in person. The first one of the workshops of the surveys were civil engineers, structural engineers, and the second workshop was conducted was with the local policy makers, for example, with local and central government officials and insurance assessors. So we looked at the survey responses of the workshops. We processed them, and then we, in terms of classification criteria, and then we created what we think is called is a first element element first ontologies, so including both reinforced concrete beams, columns, and unreinforced masonry infill walls. And with that, we identify the governing failure modes. As mentioned before, we looked only at two failure modes: flexural failure corresponding to ductile behavior, ductile response, and shear failure mode corresponding to brittle response. And with that, we can make a rapid decision whether the building has to be repaired, retrofit to strengthen, for example, or simply demolished. In terms of identification criteria, we looked at, as I said before, we looked at flexural failure mode corresponding to ductile response. Ductile response is indicated by these bullet points. I'm not going to read them because I assume that you know them. Okay. I will say only that the ductile response will imply considerable rotation capacity and energy dissipation according to reflected in the modern standards, for example, the American standard, ASCII 41 in Eurocode 8 in Europe, for example, or the Turkish practice according to TEBEC 2018. The second failure mode, the shear failure mode, corresponding to brittle behavior. The brittle response can be indicated through these bullet points. I'm not going to read them. I'm going to say that only this implies abrupt strength loss or potential reduction in axial capacity, axial load capacity of the elements, of the vertical elements, the columns, for example, according to as reflected in, for example, the American Code ASCII 41. Regarding the Turkish code, Building Earthquake Code, or TEBEC 2001, I will mention about TEBEC 2011, sorry. So according to the Turkish TEBEC 2018, will this treat seismic loading actions that are prone to brittle failure as force control, and therefore brittle elements are subjected to strict capacity checks at element level. In practical terms, what this means that the shear, the joint shear, the bond and anchorage, and the confinement related resistance must not be exceeded by the computed seismic demand for the target performance level. If the seismic demand to element capacity ratio for any primary element is greater than 1, TEBEC, this code will not permit the structure to be classified at that performance target, and the buildings must either be reassigned to a lower performance level or to be strengthened before compliance can be claimed. This philosophy is explicitly reflected in this damage limit figure shown in the slide. Highlighting, distinguishing the following stages. The limit stage, so denoted by on this slide by SH, control damage, denoted here by KH, or pre-collapse damage, denoted here by GO. According to the BEC 2018, when a structural element reaches its brittle capacity limit, it automatically moves out, it immediately moves out of the damage limited stage, out of the limit domain damage, okay? So SH or control damage into the pre-collapse damage range. This happens regardless of how much the building has moved or drifted. In contrast, or on the other hand, the ductile flexural actions are evaluated based on how much the element can bend or rotate. This element can handle some permanent bending within controlled range without immediate danger. And this is a philosophy which was used to identify our criteria, used in our criteria, identification criteria. So in this slide, you see the proposed visual guide that we proposed for the first failure mode, for flexural failure mode, in conjunction with the visual indicators and damage level. Okay. And for the second failure mode, the shear failure in conjunction with the visual indicator and the damage level. In terms of dataset development, we adopted a multi-step approach, starting with web scraping, the data segmentation, up to the version and the version control and documentation of the very last stage, documentation of the database considered. In terms of data set developed, you can see that in this figure you have just samples, a few samples of the classes considered. You can see that, you perhaps can see that the data set created, developed was rather small. Okay, as a in general, or for all the classes assumed, or you can see that we can the small number of images sourced for some classes. For example, for flexural, for beams in flexure, we did manage to find only 113 images compared to the rest, to the shear failure. Okay. To create, okay, so the previous slide, to bring this, to increase this images, this number of images, we did manage to get to use dataset enhancement. In this particular study, we used data augmentation techniques and synthetic data generation techniques. For example, for data augmentation, we used, starting from original image, we used the traditional geometric transformations, all of them, and then we used the color space augmentation techniques, and then we used noise injection or elastic transformation. As regards the synthetic data generation, we used only two methods: mixed up method and cut mix method. So in this slide, you can see that following the data set enhancement techniques, we did manage to get a total images, total number of images of enhanced data set of about 600 images, 6,000 images. If it is appropriate, suitable number or not, we shall see. Okay, all right. In terms of assessment model, we used, this is the multimodal deep learning model, assessment model. We used, this is the architecture that we used. We used simultaneously the images and the text to get at the end, on the right-hand side of the slide, you can see the output. So the failure modes. The appropriate failure modes. So in terms of damage input of a damage input of the images, we get the output. In terms of textual description, we have a concise engineer written textual description of each image to get the output in parallel. Okay, one solution for the multimodal assessment model was the use of transfer learning technique. What does it mean in practical terms? It means that the model is used using a pre-trained CNN model. So, for example, a pre-trained convolutional network model on a large data set developed not a small data set as we had, developed for another purpose, and then learning features from this data set that perhaps are common to our target data set. For the sake of in this presentation, in this multimodal approach assessment method, we use a model, a pre-trained model called MobileNet V3 large. So the classification mobile as a backbone, and the classification this model the classification layer of this model was removed. So it was practically working as a feature extractor, and then the model was fine-tuned by unphrasing. The last few layers, allowing the data set, the target data sets, to be learned, allowing the characteristics of data set of a target data set to be considered, while the other earlier layers remain fixed, remain frozen, as you can see in this slide. So we did manage to evaluate the performance, to evaluate the model performance of this model. We by confusion matrix, by plotting the confusion matrix. So you have on the vertical axis, on the horizontal axis, you have the predicted classes, the 6 ones, and on the vertical axis, on the y-axis, you have the true classes or the actual classes. The confusion matrix will have, as you can see, 4 elements, true positives and true negatives, and in conjunction with false positive and false negatives. I'm not going to mention them. So the using why we use the confusion matrix, because based on the 4 elements, we can perform we can calculate some indicators for the model performance, to assess the model performance, such as accuracy, recall, precision, and F1. And you have the definition of these elements here. You have 2 more indicators we looked at: the area under the curve and the average precision, and their formulae are given. Okay, and in terms of assessing the pre-trained, what is the most suitable pre-trained model, we looked at 2-stage approach in these 2 figures. In stage 1, we on the horizontal axis, you can see the various pre-trained models available that you found in the literature. In every single of these pre-trained models, we have convolution networks and layers were frozen. So we acted as this acted as a feature extraction. Only the models achieving 0.75 simultaneously for the 4 indicators for accuracy, precision, and recall were taken into the next stage, in the 2nd stage. So the figure, we move now to the figure B, called B. The candidate, these models, they were fine-tuned. So it means that the last layers of the model were the fine layers. The last layers were unfrozen, and you can see that among the all these models, the MobileNet model, pre-trained model, CNN model, was achieving the strongest results. So this is how we chose a MobileNet for this domain and for this application. In terms of model hyperparameters, they are normal. The hyperparameters considered as normal for this kind of domain, for this kind of application. You have here in this slide just a flavor, just to give you a flavor of these hyperparameters, just 4 of them: learning rate, for example, dropping rate, and the number of unfreezing layers for fine-tuning. We did some sensitivity analysis, so to come up with the optimum value. So for the learning rate, for example, the optimum value is 10 to minus 5. For dropout rate is 0.6, and for unfreezing layers for the fine-tuning stage is 10. And for model regularization factor is 0.02. But other hyperparameters were considered. Okay, so in terms of we adopted to see that if the model works very well or very well in the training stage, we considered five-fold cross-validation protocol, so which works very well in case of very small data sets, as in our case. Okay. In terms of damage, in terms of results for the model of validation performance, so we see the model accuracy, precision, and recall, and F1 score, so the four indicators. So we see that they are quite close to each other, so 0.2, 92 around. So this is what we want to see in case of a model, in case we have a small data set, as in our case. We can see here the model testing for confusion matrix. You see here the confusion matrix for the model testing. So the predicted level versus the true or actual or ground truth labels. Okay. And in here you have in this table, you have the model testing results, a summary of model testing results, performance indicator results, all the results for all the six classes in here. So the mean accuracy is 0.9 about. The F1 score is 0.9. Okay, recall 0.902. Precision is 0.98. So the mean accuracy is following closely what I presented in the model validation in the mean accuracy, which is 0.92, which shows a good ability of the model to generalize. Okay, I'm trying to. Okay, in the area for the area under the curve, AUC, the factor is this mean is 1, and for the average precision is 0.99. We did get. Okay, we evaluated, we did an ROC analysis, we did ROC analysis, so we did perform the curve. We showed the curve here, the ROC curve. Okay, so you can see that the AUC, which is area under the curve, is for all these classes, for all these failure modes, are almost equal to 1, which indicate a good generalizability ability of the model. Okay, the same good strong results were achieved when we did the precision recall analysis. So we plotted the curve. So for all the flexural, all the failure modes, in all these cases, we see that it's between the AP, the average precision is in between 0.95 and 1, with 0.91 the average value. Okay, and in terms of limitations considered in this study, of course, the dataset is relatively small compared in this domain and this application compared to other domains. Class imbalance, visual modality, visual input visual modality. So the model uses single 2D photos as a mean of visual means. So in terms of images, we could have 3D, so adding depth to the image, for example, or missing geometry. So there is no explicit geometric context, as I said, depth or information on the scale that refer to the damage classified. Okay, and finally, the direction of future research directions. So we need to expand the dataset diversity to add more buildings, more regions, for example, to look at various other failure modes, okay, other failure modes and element types. Okay, and then dataset enhancement, stronger augmentation, and synthetic data generation, and field deployment studies. So to validate performance, I should be very careful when I'm saying validate, because based on the feedback provided by the computing people, we should not validate. In our case, as structural engineers means something, in terms of computing people means something else. So I should say check the performance in the check or verify the performance in real conditions. Okay, mobile edge interference. For example, we can use smartphones or tablets for on-site use, and human-in-the-loop interference to ensure that engineers can interact with the model's predictions while having access to building codes and damage assessment guidelines and overall safety standards. Okay, so in conclusions, I talked about these aspects. Okay, and finally, I would like to acknowledge the contribution of 2024 EEFIT grant, research grant scheme of the Institution of Structural Engineers. And with that, I finished the presentation. Thank you.